So I just want to introduce myself. I'm Claire. I'm a third-year PhD student in environmental engineering in the Pacman Lab. And let's go around and maybe introduce the rest of the presenters today.
Hi, I'm Emma. I'm a fifth-year PhD in the Pacman Lab.
Hi, I'm Kelly. I'm a fourth year PhD in material science and engineering in the Javid Research Group.
I'm Gray. I'm a postdoc in the Dictel Lab in the Chem department.
Okay, so I already briefly talked about what we, Sarah and I both talked about what we want to get out of these presentations, but just to summarize again, today we're going to be talking about collaborations in wastewater technologies. So again, me and Kelly are doing a collaborative project that we'll talk about, and Gray and Emma are also doing a collaborative project, and both are in wastewater technologies.
Hence the name.
Yes, sorry, I'm like over-explaining the name. Yeah, we talked about the graduate cluster, and I think we just got confirmation that master's students can also take this graduate cluster, so you don't need to just be a PhD student, so it's open to everyone. So yeah, just again, Wildcats and Water is a new seminar series hosted by NU Water, so this is NU Water, to highlight research projects relating to water, and we're hoping to get undergrads presenting. We have graduate students and a postdoc today presenting, so if you're interested, please apply and fill out the interest form.
Yeah, across all disciplines,
yes.
even minorly relating to water.
Yeah.
It's very general.
Yeah, we want to hear across the board about like all things water. Specifically, we're looking for more humanities people, just because it's a little underrepresented at the moment.
And then at the end, we'll present our topic for next month.
Yeah, and we have a topic lined up for next month, so stay tuned. And it's going to be on the second Tuesday of every month, and there will always be food. So if you can make it now, hopefully you'll make it to all the ones in the future. So I think with that, let's just get into it.
Yeah, woohoo. Okay, so we're gonna go through two projects today. Oh, sorry. The first one is Gray and my project. We're talking about a cyclodextrin-based adsorbent for removing PFAS from wastewater, and then we'll hear from Kelly and Claire about their work. Okay, I don't like this. I can't stand
Do you
here.
want me to go on the other side?
Yeah, you should go on the other, right?
All right, sure.
Do you want me to do the... Sorry, it's our first one. We're
Sorry,
still
guys.
doing all the...
Okay.
Working out the
Yeah,
logistics.
Yeah.
Okay, so a little background for people who are not familiar with PFAS. Raise your hand if you've heard of PFAS. Nice, wow. Honestly, I feel like if I had been giving this presentation 1 year ago, it'd be half the amount. And then 2 years ago, maybe one person would have heard about PFAS. It's like blown up over the last year or the last couple of years. So for those of you who did not raise your hand, PFAS which stands for per and polyfluoroalkyl substances, are a large group of over 10,000 human-made chemicals. They're characterized by a carbon-fluorine bond. So for chemists in the room, you know that's a very stable bond. I think the hardest bond to break. Is that correct?
I think it's the hardest heteroleptic bond.
There we go. As you can tell, he's the chemist. Contributing to stability and resistance to degradation. So when they're in the environment, they don't naturally break down. And approximately 45% of U.S. tap water contains one or more type of PFAS. And even at extremely low concentrations, these are toxic. That was also a report from USGS in 2023, and that hasn't been updated, but I'm sure it's higher now. So this is an example of what a PFAS compound looks like. So the issue here is that PFAS-containing products, which you can see some examples to the right, pollute water that's entering wastewater treatment plants, and conventional water treatment processes do not remove PFAS.
So what are these conventional treatments that we've been using to get rid of PFAS? Since they don't degrade on their own, we need some sort of intervention to remove them. And the main ways that we've done that have been ion exchange resins. So these primarily function with electrostatic interactions. So just looking at the charges, most PFAS have a charge, and just trying to use that charge to get rid of them, kind of like a magnet. But the issue with that is that water sources, whether it's wastewater or groundwater, they've got a bunch of other charges in them, like salts and stuff that you'll find in drinking water too. So when you've got other charges in that water source, that's kind of inhibit the ability of these ion exchange resins to get rid of PFAS. So they're pretty prone to fouling from that. They're also more expensive than other conventional removal systems. Things like activated carbon. This is actually the most often used strategy to remove all contaminants, PFAS included. It's the cheapest strategy. You can get a kilogram of activated carbon for just a couple dollars, but it's really not very effective. It's also not specifically targeting PFAS. It targets pretty much all contaminants just with a really porous structure. So it'll bind to PFAS, but it'll also bind to any other thing found in water, things like humic acid, which are just naturally found in water and aren't necessarily going to be toxic. They're more benign. So our strategy revolves around these styrene functionalized beta-cyclodextrins. So beta-cyclodextrins are really commonly used industrial chemical. Things like Febreze have beta-cyclodextrin in it, and that's because it can target different compounds that have a hydrophobic component to them. A lot of odorous compounds have a hydrophobic component to them, just like PFAS does. It has kind of two main components, a hydrophobic tail and a hydrophilic head group. So our strategy targets both that hydrophobic tail and the hydrophilic head group, unlike things like ion exchange resins, which are only targeting the hydrophilic head group. And that allows us to not only have a higher affinity for PFAS, but also increase selectivity by mitigating influence from things like salt. Because when you're targeting a hydrophobic head group or hydrophobic tail group, you're going to remove influence from salts, since those are really highly hydrophilic and they're very polar.
I'm gonna set a precedent for asking like really basic questions because some of us really understand what you're talking about.
Yeah, and please
Some of us
interrupt.
kinda
Yeah,
like,
you
Yeah.
can interrupt.
That second box, we've kind of lost us. So
I'm gonna, and for non-chemists in the room, basically these beta-cyclodextrin adsorbents, they not only adsorb by electrostatics like ion exchange and hydrophobic interactions like activated carbon. It does both of those. And then it also has a third mechanism where it's shaped like a cavity that's actually the exact size for some PFAS compounds to dock inside of it. So it has that electrostatic, the hydrophobic, and then this additional cavity where you can see it docking inside. And because it has all of those different modes of adsorption, even if some of those are inhibited in certain water matrices, there's additional modes of removal. So
that was super clear. Not that was.
Thank you. That was probably
that's the engineering explanation.
And I'm thinking of like an icon where you have like a superhero, like three superheroes. Where one is the ion exchange superhero, one is the activated carbon superhero, and the other is the like castle-shaped hero.
Wow. Okay, love it. I'm gonna make a new graphic.
Yeah, we can make a.
But I thought you did great.
Thank you. No, that was
Yeah, I mean,
probably a more simple explanation. All right, so our original strategy for making these Sidex-based adsorbents was basically just making one big block and then crushing it up into a powder and then running water through that powder. And that was a very effective strategy. We were able to remove tons of PFAS with that strategy. But the issue is that when you run water through a really fine powder, you can't really use high flow rates. You're going to lead to a lot of high pressures, and it's going to slow down the flow of water. So you couldn't just insert this into an industrial process and continue those same flow rates. It would slow down and lead to clogs and high pressure. So we wanted to move away from this powdered strategy and synthesize something like beads. One way to do that would be to granulate it. So you could take the powder and add in some sort of binder and turn that into bigger clusters of powder, which is what they do with granulated activated carbon or GAC. But then you're adding in fillers and things that don't actually bind to PFAS. You're just adding in pretty much dead space. So a better route to go would be a dispersion polymerization, which is on the next slide. So we needed to kind of change this synthesis a little bit. Instead of just making one big block of polymer, we needed to make little droplets of it and then turn those into beads. So our strategy revolved around this dispersion polymerization, where we've got an aqueous layer, which is just water with some salt and other organic components, and then an organic layer. And that organic layer, the key is that it's not going to, it won't be miscible with the water, so it won't mix with the water. So when you combine the organic and the aqueous layer, you end up with something that kind of looks like a salad dressing, where you've got little droplets of organic layer in that aqueous layer. So then we stirred those for a couple minutes and got stable droplets there, and then exposed that to UV light. And since we've got our AIBN initiator in there, that's going to cause those droplets to polymerize and then form little beads that just look like white kind of clumps of powder. Yeah.
AIBN initiator, what is that?
It's a radical initiator. So when you shine UV light on that, that's going to break apart and you'll form two radicals that will then react with our Stydex monomer through those styrenes, and then 4-vinyl benzoyl chloride also through that vinyl group right there.
So right now in the salad dressing,
Yeah.
is the aqueous. It's a water, polyvinyl alcohol, and
Salt. Yeah.
And then
Yeah.
in that silver thing underneath it, is that where those beads are? The beads of the.
The beads are these
Yeah.
yellow droplets.
Oh, they're.
Yeah, they're
that.
in the aqueous layer.
Okay.
Yeah.
Other questions? I'm sure I'm not the only one who has questions.
Yeah, feel free to.
Feel comfortable.
Yeah.
So how does this, I guess, benefit like an industrial process? Is it so that you can make a giant vat of this?
So you can use larger particles and then run higher flow rates through them. When you're using something like a powder, it's really hard to push a ton of water through that. Whereas with larger particles or beads, you can run a ton more water through. The beads are about. Or you can
Oh, I was gonna say, but as for scaling up the manufacturing process, we're still working on that.
It's still yeah.
Not completely related, but I'm curious about like reverse osmosis. Is that something that can't be done at scale? And is that actually effective in like removing?
It's very effective at removing PFAS. That's a great question. It's hard to scale though. It's more suitable for like household use.
Yeah.
For industrial applications, it would be expensive and slow. Yeah.
Yeah, and then like for wastewater, for example, which is what we're targeting, it'll foul really quickly because there's so much other stuff in wastewater. So that's the biggest issue with like RO or other technologies, is that when you try them in a complex water like wastewater, it just like stops working immediately. Yeah.
How reusable are these beads?
Oh, stay tuned for the last slide.
Sure.
But really good question.
Okay.
Yeah. Oh,
Sorry.
I'm sorry, I should have asked this question earlier. Where do you differentiate a fluorinated carbon compound from being a PFAS?
that's really broad. There's a lot of different definitions of like what is PFAS. Some definitions would say there's only 900 PFAS. Other definitions say there's 10,000, which is what I had said. So it depends how you define a PFAS. So it really can range between 100 to 10,000 compounds, but different places have different definitions. So you'd have to look into it. Yeah.
Is it PFAS or PFAS?
I say PFAS. What do you say?
I always say PFAS, but I feel like most
You say
people
PFAS.
PFAS. I feel like most people
So,
say
because
PFAS. I don't know.
PFAS with an A, there's also a PFAS called PFAS with an O.
Okay.
So not to be confused with. But you can say whatever.
I'm just kidding. Please continue. Great questions,
I think
everyone.
there's one more.
Yeah.
I just
Yep.
have one more question. You kind of started by saying that like PFAS has now become more commonly understood. Do you think that like most manufacturers aren't treating their water for this right now? Or
Not really. No, there's
Yeah.
really limited treatment
So drinking water, there was a regulation
starting in
last
2031,
year.
I think.
Yeah, it was for 2027,
I
but
thought
it was
2031.
just pushed back. Yeah,
Yeah.
It's now drinking water plants will have to treat PFAS, but not till 2031,
A
down
lot
to
of
certain
companies
levels.
are moving away from it, though. It used to be in like water repellent clothing, but companies like Patagonia, which I guess you could expect would move away from that since they're kind of a more outdoorsy and observant company. But industries like semiconductors, they can't really get away from PFAS, so this isn't really gonna go away anytime soon.
Yeah, and they're not being forced to. So some companies are opting to, like Patagonia, but most companies aren't actually being enforced to.
What about fire extinguishers?
Well, the DoD published something last year that said that PFAS in firefighting foams are essential to national security. So I'm not sure if we're getting away from.
Well, the administration seems really sympathetic to
Yeah.
environmental issues. So.
We're being recorded.
Fine.
So now I'm going to go into a little bit about our testing approach. So Gray has done all the synthesis and materials discovery, and then I'm doing testing. So we're doing rapid small-scale column testing, or it's called RSSET. I don't know if any of my slides say that, but just defining it in case. So basically what we do is we pack a column with Gray's beads in a certain size range, and then we get wastewater from MWRD O'Brien plant in Skokie, and we spike PFAS into that. there's not high enough levels of PFAS in the wastewater already, so we have to spike our own. And then we run that through the material and see how well it removes the PFAS. And then what we get after that is we're able to construct what's called a breakthrough curve, and Claire will share some of these as well. And what it shows is that over time, that the concentration coming out of the column starts to gradually increase. So here, this is the concentration that's coming out versus what we're putting in. So you can see, for example, for some compounds, it has really high removals for long periods of time versus other compounds have really low removals, and they have fast breakthrough, meaning that we see them in the effluent very quickly after we start the experiment. And that's because all PFAS are different. It's a large group of compounds, and they all have different chain lengths, head groups at the end, and other things that make them different from each other. And so some are a lot easier to remove than others. And so that's another thing we're looking at, is what we're able to remove, what we can't remove well, and why we can't remove it, and eventually how to overcome that. Yeah.
So the different curves there are different, specific
Yes. Yeah, I don't know why I didn't label it. But yeah, so every different color is a different compound that we're looking at.
A different PFAS.
We're actually also looking at pharmaceuticals because PFAS exist in complex waste streams where you have a lot of other stuff in there too. So we also wanted to look at how we're removing other things at the same time. So we're looking at 2 pharmaceuticals and then 5 PFAS. But you can't look at all 10,000. That would be really hard. And then what we've done is we've constructed a pilot scale test at the wastewater treatment plant. So in the previous test, we go pick up water and bring it back to Northwestern. But I'd have to bring so much water back to Northwestern to do that. So thankfully, MWRD has allowed us to set up testing on site. So we basically run the exact same test, but at scale with the largest size of bead that Gray is able to manufacture. And then we run these tests for about 3 to 4 months. And then the goal is to then be able to establish a relationship between the lab scale and pilot scale tests and be able to estimate what we would see in a pilot scale experiment without having to run it for 3 to 4 months. So in the lab, we could run an equivalent experiment for about 10 days, which is way better for a PhD student who can't run an extremely long-term experiment. And then lastly, we're also looking at regeneration of this material. So it's very regenerable, and it can be regenerated quickly in an alcohol solution. And what we've seen is that the PFAS are actually regenerated even better than other compounds that are on the material, which is positive because we're addressing PFAS, but negative because now we also need to figure out how to get everything else off. But you can see here that the dark lines are how much was removed in the experiment, and then the striped line is how much was then regenerated and recovered off of the material. So for some of these compounds, we're getting really high recoveries of like 99%. And that's something that we're continuing to optimize. Do you have anything to add?
I think you got it.
Okay.
All right. What do you do when you remove the PFAS from the Stydex?
Do you want to speak to that?
It can be destroyed just with heat and base, adding that to the regeneration solution.
Okay.
There's a couple of commercial destruction technologies that destroy PFAS in alcohol, salt, like in a solvent. So there's some that are methanol and IPA, I think. We use IPA. So what you'd be able to do is like put this solution into one of those destruction technologies, and then it would destroy it there.
It breaks it down all the way into like fluoride and then some carboxylic acid carbon-based compounds.
So pretty harmless stuff.
Yeah.
Mm-hmm.
Thank you. That was fantastic.
Yeah. And we can, after their presentation, we can ask more questions. Or now you know where to find Gray and I.
Or are there any questions right now? Hugh has a question.
Just curious about the sort of manufacturing process for this. Are there waste problems with that as well?
With manufacturing?
Yeah.
I mean, there's always going to be waste problems with any chemical process.
Of course.
It's mostly water. I mean, because when you make the beads, the biggest byproduct is just that aqueous layer. The organic layer is pretty minimal. Making the monomer, there's some solvent use, but I think in an industrial process, you could potentially reuse that solvent with like distillations. But we haven't really gotten to that point quite yet.
And Gray is working on how to manufacture this in the most effective
like a
way.
more
That's sort of what he's
scalable
looking at now. Cool. Thanks, guys. Oh, yeah. Yeah.
Question. And I'm not from a STEM background, so this may be an ignorant one.
No such thing.
I appreciate that. I've been in conversations where corporates are talking about PFAS, but then they also bring up the subject of microplastics. Do the two like intersect in a Venn diagram, or are they completely separate?
They would be treated completely differently.
Yeah, microplastics I don't think actually dissolve in water, right? They're like more of like sediments.
Yeah. It's more of like working on like solids. Alex works on some microplastics. Maybe you can ask him.
Thank you.
Thank you.
All right.
Let's see how it works and see what I can do.
Let's try. Yeah.
I'm gonna see if it stays if I leave it. I'm gonna see if I can use the mouse.
Did it work?
Yeah, it worked for that at least. So,
Okay.
anyways,
Nice.
if not, then I'll ask for your help. Cool. All right. So yeah, now we're going to be shifting gears a little bit. We're still looking at wastewater, but this time we're looking at a different type of pollutant. So we're going to be looking at phosphorus, and we're going to be using iron oxide cotocellulose sponges for the recovery and reuse of phosphorus from wastewater. So a little bit of a background of the effects of phosphate pollution, and taking us to a lovely map of where we are. We are here right now, but as you can see here, that's Lake Erie. And you're wondering what that green stuff is. It's very pretty, but it's actually very bad for the environment. And those are algal blooms. And that is caused by phosphorus and nitrate runoff that's coming from agricultural-based fertilizers. And those fertilizers go into the water, a bunch of microbes, they want to grow with them, and they overgrow, and then they create these toxic dead zones where there's not enough oxygen for any life to be as well. So excess phosphorus in the environment is very detrimental to the environment. And as Claire's about to talk about, since we're using them in these agricultural fertilizers, there's something that we really do need to be able to grow enough food for everyone. So treating it not as just something that's a pollutant, but instead as a resource is something we're trying to change in this paradigm as well.
Okay, so I'm gonna pull in Emma. So who's heard of like eutrophication, like what we just saw? Okay, and then who's heard of like phosphorus mining? Okay, a decent amount of you, but like we dwindled to like half. So basically what's happening right now is that there's this ore called phosphate rock. So it's mined and it's turned into phosphoric acid, and then that's what's used in fertilizers. And then it's applied to soils, and then some of it like runs off into waterways and causes eutrophication, which is bad. Some of it ends up in our wastewater treatment plants and then is kind of discarded as sludge and waste, which also turns out is also bad. So we're kind of, right now there's a linear phosphorus economy, and we're trying to change that and turn it into a circular phosphorus economy. So for some reasons why what's currently happening is bad are, phosphate rock mining causes greenhouse gas emissions, and there's a really large energy consumption from the mining. The ore is only concentrated in a few countries. I think over 80% of phosphate rock is present in Morocco. So you can kind of imagine how once the supply starts to dwindle, there's going to be a monopolization and prices could rise. Moreover, like I just said, there's only a limited amount of phosphate rock present in the world at this moment. So once it runs out, the global food supply could be fertilizers costs could go up, and then food could go up, and then it's just a whole bad cycle that we don't want to get into. And then as we use more phosphate rock, we have to use more that have ore impurities, which can end up in the food supply and be detrimental to human health. And also there's a large production of waste byproducts when you convert phosphate rock to phosphoric acid, which is what is used in fertilizer, and that's called phosphogypsum, and it's also treated as a waste product, and 5 times the amount of this waste product is produced for every unit of fertilizer. So it's kind of a really wasteful cycle that we're in right now, and the goal of our project is to kind of fix this and create a circular phosphorus economy. Oh, and this is why we need.
Yeah, so going into how we're trying to contribute to this circular phosphorus economy. So metal oxide, specifically iron oxide in the form of magnetite or Fe3O4, it has been known in literature for years and years to have this really strong interaction with phosphorus. And this interaction can include things like bonding to like the oxygen here. And we know that it is also very selective towards phosphate as opposed to other ions in solution. So previous research in my group, step back. So these metal oxides, we have them, but when we're trying to, sort of similar problem to the powders like the cyclodextrin, just having a metal oxide powder and trying to flow water through that is not very good for like these larger applications like wastewater. And magnetite is, like in the name, magnetic. So how it's been used currently is that they use a magnet to be able to separate out the metal oxide from the clean water that it then generates. But that's not going to be very good. It's very energy intensive. So it's really hard to scale and deploy that type of technology. So research that's been done in the Dravid group was trying to look at, okay, how can we use this really great metal oxide in an actual deployable way? So we do that by creating this sponge nanocomposite. So iron oxide has a lot of these hanging oxygen groups and the hydroxide groups. So it hydrogen bonds to the surface of cellulose very well, such that even though, even if you were to put it in water, the iron oxide is going to be staying onto the surface of the cellulose no matter what. It's sort of like, I kind of think of it as almost like a paint. Like if you paint something, you get a stain on something, like that's not coming out. It's very similar in terms of the iron oxide that you're seeing on the sponge there. So we have this high surface area from the cellulose sponge, but then the metal oxide also has a really high surface area for all of this phosphorus to be able to absorb to it. And taking an even closer look, this is a scanning electron microscope image, or SEM. And what we're seeing here is you can see the porosity of the sponge, and then you're seeing all of those little white dots everywhere. That's actually iron oxide. It's showing up as the opposite color under the microscope because iron has a higher Z number, so it's more heavy. So it's going to actually give off more electrons when you shoot electrons at it, which is going to make it show up brighter. So in this image, we're seeing how the iron oxide is sticking to our cellulose, and we're having that hierarchical porosity there as well. So going into the material properties and how we're actually using this to then capture phosphate. So first, it has this great selectivity. So iron oxide, like I was mentioning, is selective towards phosphate and not any other anions in solution. So this water was also from MWRD, and this was looking at all of these other ions in solution. It does not absorb a fluoride, bromide, nitrate, sulfate, or chloride, which are all very common in wastewater. So to be able to show this great selectivity just towards phosphate is really great for this application as well. And the other great thing, which is how we're getting more into the recovery component, it's one thing to just keep getting phosphate, but we want to actually get that back to be able to reuse it, is that it has this pH-dependent sorption mechanism. So the plot that I'm showing on the right is looking at how much phosphate can be captured on that y-axis versus what pH the solution is in. So when we're at a very acidic pH, we're getting very high capture rates. And even when we're at pHs that are a little bit more neutral, like what we're finding in wastewater, like maybe that 7 range, we're still getting pretty high amounts of capture. But as soon as we push that pH towards more of a basic pH, then we're getting much less capture. So you can imagine that if we take something that's in a pH 7 solution and then we just change the pH on our own, we're able to then get desorption that we can then change and get the phosphate back. And now I'm going to give it over to Claire about how we can actually get this going in applications.
So my purpose in the project is to, try to optimize the material in lab. That's kind of what my current research is focusing on. And then we're planning on doing something really similar to what you saw with Emma's work and start a pilot program at the local wastewater treatment plant. But first, we kind of need to study the material at lab and kind of see what are the most optimal kind of variables that we can change to see, one, the best removal of phosphorus, but also the best recovery. But first, before I talk about that, I want to talk about how calcium kind of interacts with the material and phosphorus in solution. So we've seen in testing that similar to other iron oxide adsorbents, calcium really increases the amount of phosphorus that the material, or iron oxides in general, can remove phosphorus from solution. So this plot is just highlighting that. I think we saw like almost double the amount of phosphorus was removed when calcium was present. And we're also seeing that in the adsorption solution, calcium is also being removed. So that tells us that there's some kind of interplay in between calcium and phosphorus and the surface. And we can't exactly say, we have some theories, but we can't exactly say what's specifically going on. But we do.
Very quick question.
Oh, yeah, go ahead.
Would you mind explaining what the organic matrix column is?
Yeah, so this is just because we're studying wastewater first, I wanted to isolate the inorganic effects before like we add all the background noise in wastewater. So this is just a representative matrix that I made with the major ions in wastewater. So it's just a bunch of ions that like it's kind of like a recipe that I add to water and I test with it in the lab. Yeah, but that's a good question. So it has the same amount of calcium as what I put in this solution. So this is just going to show that most of the effects are kind of due to calcium. Yeah, so calcium is also being removed, and then we see these kind of clusters of calcium on the surface of these EDS images that Kelly took. So yeah, this could lead to issues down the road when we have these kind of like coating of calcium of the surface. So that goes into what I'm studying now, which is there's some animations that we, kind of trying to optimize the recovery of phosphorus. So I won't bore you with a lot of the details, but the goal is, since we're trying to optimize the material in lab and kind of get the best bang for our buck in terms of recovering phosphorus, we want to test a wide range of variables in the lab. So this was just an example of something that I tested. I did an acid wash to kind of try to descale the surface, which is pretty common. I think maybe you might have heard of it before. Like you try to descale pipes and stuff from calcium precipitation. So yeah, this was just an experiment I did, and we found that pH 4 kind of gave the best recovery of phosphorus, and it also led to the least amount of iron being leached into solution, which would be bad, and a decent amount of calcium was removed from the surface. More animations. And then finally, I'm just going to talk about, this is a really similar slide to what Emma had, and it makes sense because we're kind of aiming to scale up to the same sort of testing. So this flow-through testing, basically, we're able to kind of test what maybe what the material like application would look like in a larger sense. So imagine just like larger columns. So the influent is, upflown through the column with the material, and we can change the different type of shapes that the material takes on in the column, and we can compress it differently, which I think is kind of something that's really cool about this material, is that it's a sponge. So like if you think about it, you can kind of fit a bunch into a small space just by like pressing it down. And yeah, we can change the influent solution, so we can kind of cycle through an adsorption, an acid, and alkaline wash. So we see, similar to what Emma was showing, we see the removal of phosphorus in the adsorption solution, and then it reaches a breakthrough point. And then with the acid wash and the alkaline wash, we see the release of phosphorus in these concentrated solutions, and then we can recover the phosphorus. So yeah, that's what I've been working on, what we've both been working on.
Mm-hmm.
How much phosphorus is in our wastewater here?
That's kind of an issue that we've been dealing with. It really varies, like depending on like wastewater treatment plant season, place, like location, like what are the state's guidelines. We see like typically around like 1.5 ppm, milligrams of phosphorus per liter. Some places can see up to 5, but the problem is that the government which is good, states are starting to impose more strict guidelines to protect against eutrophication. So wastewater treatment plants are really trying to tackle like how do we get below like 0.5 milligrams per liter. So they're starting to implement more and more technologies to get the levels to be low. Yes. Do you want to continue? Or okay, Joaquin, you go first.
Is it a priority for wastewater treatment plants to not only reduce it but to recover it?
So actually, I thought that it was more. I thought that everyone was on the same page, like that it was like, okay, like we're running out of this like material that we're something bad is really gonna happen. But it seems like right now with the economic cost of mined phosphorus versus recovered phosphorus, it's just we're not able to compete at this point. So that's why it's important to kind of work on like optimizing the materials that we do have to kind of make it cheaper. But yeah, so right now I don't think that it's really a priority for people to recover it or wastewater treatment plants because of money. Yeah.
Are there biosensors or some sort of rapid test for detecting phosphorus?
Yeah, there are. We don't use that just because we want to be like precise with but yeah, you can find like handheld like sensors.
It's like the pH. It's kind of like a pH
Yeah.
color stick.
Yeah, you can use those too.
Oh,
I don't know what
no,
they use. I think they use analytical methods. as well.
Yeah, because they release the data. Was it like weekly that they give us data also that you can look up like how much phosphorus is in the wastewater?
Yeah. So
plant
everyone
weekly.
can go look up like for the past like I think 50 years or something. Like it's they do daily monitoring because they need to like be. I think they have like monthly averages that they need to like be below. So yeah,
that's where that's where Claire has also found how much calcium is in the wastewater. So she's been able to dope these with the amount of calcium that's in wastewater, so we can understand how that's interacting with the phosphate as well. So it's cool that we have that much data.
Yeah, no, it's a really good resource. Yeah.
Do you talk with Garrett much?
On a social basis.
Because this is what like with the Lux Lab, what we're doing with.
Oh, I didn't know that.
He's talking.
I know he's doing like sensing for lead stuff. Okay.
No,
I should work with him.
Oh, no, too bad he's at the dentist, right?
Yeah, I know.
But this is useful.
Yeah.
So there was a seminar talk not last Friday, but the Friday before that was all about phosphate, like PAOs.
Yes.
Phosphate accumulating organisms. And so how does this complement that work?
Yeah. So I think so basically this material is best suited for a lot of the a lot of the material is best suited for the technologies that wastewater treatment plants they work at higher concentrations. So this would kind of be used as more of like a polishing effect. Like under a lot of the technologies don't work well past like 10 ppm, but this can like works almost better maybe because it's an adsorbent. I believe that to kind of tackle this problem, we'll be using like multiple methods of phosphorus removal and recovery at like every single waste stream and every single kind of point source.
Is there also just a benefit of working with something that's a material versus organics that are bacteria?
Right, because that's more I think those are really sensitive to kind of pH changes and influent concentrations, like what's like in the wastewater versus this has shown selectivity towards phosphate over other ions. I mean, it definitely is pH dependent, but not so much so that it won't work if it's like pH 7.5 or like 6.5. I think there's a question over here. Yeah.
This is not at all related to like the technology.
That's okay. That's okay.
But so in terms of like the eutrophication and like runoff, my understanding was the majority of like phosphorus runoff, like in subsequent eutrophication, is like due to runoff. Like it's not related.
Yeah.
So like I was wondering, do you know what a percent like comes from wastewater treatment?
I actually think that it's higher than you would think, because wastewater treatment plants, like the phosphorus from those come from like human waste, phosphate kind of detergents and cleaning products, and also kind of stormwater runoff. But it's a point source, and the levels at which wastewater treatment plants are releasing phosphorus into the environment are higher than kind of what a polluted lake would be, if that makes sense. But because it's mixing like with other waterways like in the environment, they're kind of able to get away with it. But if you were to kind of just have if the concentrations at which we were releasing phosphorus into the environment were like in a standstill water, there would be phosphorus pollution, basically. So I guess I don't know the exact percentages, but I think it's more than people are led to believe.
Yeah, and I've thought of it as sort of like wastewater is like a constant, like you're always getting that phosphorus pollution versus like the agricultural ones are like very seasonal too. So exactly.
Thanks to eutrophication concerns, there's been a lot of work on ag runoff. Especially
like tillage and
Chesapeake Bay.
I think just as you presented this work to Ella and others' point to say like, okay, we think often of fertilizers being the phosphorus source. However, in our own and then reminding people that it's also like laundry and it's also poo-poo and it's also all the other things and then it's constantly coming point source thing. I think that helps put into context.
Right, and that's not to say I think agricultural runoff is totally we need to address that. I think they're just we need to address both, basically. Not to saying that you weren't saying that we don't need to address it, but I think we need to do every single point source, basically, or source.
And the proportion of phosphorus that comes from these different places to help us to see we homeowners are also culprits.
Yes, exactly.
There was a recent PhD student at Northwestern that did a model of phosphorus phosphorus, and she found that in the Chicago area, it was wastewater that really was like the leading factor, and
that's
agriculture.
Yeah, you
was,
should. You should give me
Yeah.
that info.
Mhm.
Oh,
It
nice.
was super interesting how this up until then I had heard.
I know,
about
it's- I think
agriculture being
people think
the
that,
biggest
yeah.
polluter in
Mhm.
this, but it really opened my eyes to wow, how much cities influence this because
Yeah.
of water.
There were like 3 hands over there.
In terms of this being a circular system,
Yeah.
how is the captured phosphorus returned
Yeah.
to the system? Is the end goal for it to become fertilizer again?
Yes. That is the end goal. So basically when we have this concentrated solution, you can kind of precipitate out the phosphorus by adding different forms of salts. So then you would have this precipitate that you would then in turn be able to apply to like crops basically. Yeah.
One exception for the room, there is no conventional phosphorus treatment system that exists, correct? Or
Conventional no wastewater treatment plants. Yeah, sorry. To be clear, wastewater treatment plants reduce the influent P concentrations by like a lot, but they don't usually focus on the recovery.
Yeah. I think the influence like 6 milligrams.
I think it might be even higher, like 8 or 10 or something.
Okay,
Yeah.
6 like in that bag.
Yeah.
So they decreased it by.
Yeah. And that's through like settling out and like biological processes. Like the local wastewater treatment plant has EBPR, so they use the POWs that you were talking about. Yeah.
I'm trying to formulate a question. I'm obviously failing on this, but I've been looking at this for this whole talk, and I'm just thinking that that's bog iron.
What, that we're not recovering it?
No, that what you're using here is basically bog iron.
Bog iron. I don't think
so
I'm familiar.
Bogs will accumulate iron oxide.
Oh, okay.
Large deposits in them, and that early iron working is generally done on the iron ore, basically dug out of peat bogs.
Oh, interesting.
I thought you were saying it's like horseshit.
That is exactly why I was like, I haven't heard that saying before, but like, yeah, I agree. Yeah. Wow. Nice. Yeah.
And so I'm wondering about like if the same chemical processes are going on.
Probably.
Yeah, absolutely. Yeah, it's really about like the deployability of like taking things like that we already know are happening like in the environment, and then making it, like engineering it into something that we can actually then like deploy and use. But yeah, I've gotten that comment before actually.
Oh, really?
So yeah.
Nice. Yeah.
Yeah.
Okay, last question. Anyone? Well, then I have an edit to make on my announcement about the graduate cluster. I said it's for PhDs, but it's also for master's students, and I think all the master's students who were here had to leave. So we will edit this to say it's for master's and PhD students.
I actually made an announcement at the beginning of all the presentations.
Oh.
While everyone was here,
Where was
I think we had pizza.
Okay,
Pizza
great.
help.
Awesome.
Oh, okay. Thanks. I couldn't find this. Okay.
Let's officially,
Yeah. Thanks, everyone.
the-
Oh, and this is the next.
Yeah, this is next month.
Yeah.
And
Good,
then if
excited
you'd like
on
to present, we're looking for presenters.
Use the QR
Thank
code.
you for bearing with us and being here for our first one. So hopefully it gets
It's a
even
landmark
more
moment.
Yeah. Yeah. Okay. Thank you.
Awesome.
Thank you.
Thank you.